Okay, so welcome to section two, where we're going to quantify and visualize changes based on the data that we cleaned up and imported earlier. So we're going to be creating a split panel map, and we're also going to be creating a time series graph comparing an average of NO2 concentrations for March 2019 and March 2020. So this is going to be using code checkpoint A14B. And basically, we're going to compare the median NO2 concentration during March 2020 in the Hubei province when it was in lockdown with the median value during March 2019. We're going to use this split panel, as you can see, to compare the two median composites side by side. And then we're going to quantify those changes through a time series chart, as I just mentioned, by calculating the mean NO2 concentrations for Hubei province. And we're going to be using reduced regions, and we're going to apply those to the image collections for year 2019 and year 2020, and using the same month. There's a reason for that. So we'll talk about that more as we get into it. So let's just exit this and go. So the first thing we're going to do is copy paste our checkpoint into our own script. So that's going to load, and that's just going to allow us to, if ever you're changing anything, you're not changing the code. So then we're going to go under checkpoint, section 2, and then we're going to copy and paste right below. Okay, there you go. And then again, I'm going to take my camera off just so we can look at the code in more detail, and I won't hide anything. Okay, so let's start looking at the code. Here we're going to be testing to see if we can visualize a change in NO2 concentrations during the 2020 COVID-19 lockdowns. So I'm going to go over it briefly, explain some sections, but we're not going to go in much detail. But we're going to compare the median NO2 concentration during March 2020, again in the Hubei province, with the median value during March 2019. March 2020 is the lockdown, and 2019 is going to be our baseline. So before we start, this is something that you've probably heard a lot in other chapters, but it's important to note that weather can significantly affect air pollutant concentrations, like wind, could cause, for example, long-range transport of smoke, and the variations that we'll observe between 2020 and 2019 could be influenced by changes in weather conditions instead of indicating true difference in the data. So the results that we'll be looking at might have been skewed by the weather in some way in each year, making it look like there are significant differences when really it could just be because of environmental factors. But as a solution, as you can see, we're comparing the same month in different years. And this should partly control for the effects of seasonal weather patterns, but of course, nothing is perfect, so I won't do that completely. If you, however, want to control for weather effects more thoroughly, there is a chapter in the resource in the chapter itself. Venture AL 2020. If you look at that, you should get more details on that. And in this code, we're going to be using a split panel as well, as I had mentioned from the slide, to compare the two median composites side by side. And this makes use of Earth Engine's comprehensive library of user interface widgets. And more details can be found about that in F6. I'm in section A right now, but if you look at the general book in F6, in advanced topics, F6.3 will have more details about how there are different user interface widgets from Earth Engine. So I invite you to look at that if ever you're looking for details. Okay, so let's look here. So first we're defining a lockdown NO2 median. Let me just close that so we have more space. Median composite. This is for the lockdown 2020, and then we have the baseline 2019. And then this is how we're creating the map widget. We've got our left map, admin select centering on this area basically that we had created in section 1. And then you've got hybrid that'll give you both a satellite and normal view. And then we're doing the same for right. So we're just basically building the panel here, and then we're creating in here with the horizontal orientation. And then the linker is just allowing you to link the left and the right that you created. And this is allowing you to link 2 or more maps. And then we're making a function to add a label with fancy styling. This right now is just a function, but you'll see that this comes back basically when we want to add a label, for example, to identify if we're looking at the baseline or if we're looking at the lockdown. So this is why this is important here. You're making your function in your make map lab and your label beforehand so that you can then use it later. And that's the whole point of the efficiency of functions. Then you'll create your baseline map layer and add it to the left map because the left is going to be the baseline layer, which is 2019. And again, see what I just said, make map lab. This is what you created here, your label function. So that here all you have to do is add your baseline. Sorry, I thought it was running. And then top left. And then again, you're doing it for the lockdown layer. Now, if you notice here, you've got NO2 baseline and you've got NO2 viz. NO2 viz is something we created in section 1 where we wanted to visualize the median. This is it. This is your visualization. So this is what you should be seeing in terms of palette. And then you've got NO2 lockdown and NO2 baseline. And this is what you created right at the beginning with your composite based on the dates you selected. So here in this case, we're doing March 2020 to March 2019. Once that's created, make sure you see we're here we're adding the left map, or adding the label, and then we're creating our layer. In this case, we're doing the reset because what it's going to do is that it's going to clear all existing layers from the left map. And then it's going to add a new layer, which in this case is going to be our NO2 baseline layer, which is just created with this variable. And this is ensuring that only the specified layer is displayed on the map, and that's going to prevent any previous layers from cluttering the view. And then we're going to do the same thing for the split panel to make sure that we're resetting everything so that we only see the split panel and we're only getting our baseline layer and our lockdown layer and their respective sides. So by using reset, you're just saying remove everything and just show this new layer. So now left is our baseline, right is our lockdown. This is what you're creating here. And this is what it's explaining here, that you're resetting the map interface here. You wrote widgets, reset to slider panel. So in this case, we're resetting this setup to the slider. And there's two ways this widget can go. There's the wiping effect, where maps are overlaid on top of one another. And then there's the side-by-side comparison, which is what we're going to use based on our context. So basically, this is just what we need for our chart. And we're going to run to get our split panel. So as you can see, first off, you've got your split panel side-by-side comparison. Now the layers are going to take a bit of time to load, but you've got your label, as I was mentioning earlier. And now you should see a difference. And that's what we're going to examine first with observations. And then you can ask yourself questions. There are some in the book as well. And then we're going to explore the differences in NO2 concentrations as a chart. Because while you can visually observe, it is important to have somewhat of a chart to help you understand in a more quantified way. So in this case, we have a split panel map that's showing the tropospheric NO2 concentrations over Hubei province. We've got March 2019 on the left, and we've got March 2020 on the right, which is just taking a bit of time. The hotter colors, as we talked about in section 1, are going to have higher concentrations of NO2, and the cooler colors are going to have lower concentration. Already you can kind of see that there's somewhat of a visual observation that can be made. So, say we're comparing the two right now, just from observation. Do you notice a reduction in NO2 concentrations during the lockdown? Got our lockdown here. You've got a massive center here happening of hot colors, which means high NO2 concentrations. And then when you look at that same dense city center, you've got almost no hot colors. It's mostly cool colors. So that already indicates for the same month, although considering weather effects, major differences. Because then it's like, is this change significant at all? Well, we're going to build our chart and see if there's any big changes. And where is this happening? Mostly. And what you can look at now we only have one layer because we reset it. But what's important to look at is if we remember correctly our colors beforehand, most of the population count kind of aligns with this NO2 concentration. And when you think about the baseline and the lockdown, it could mean that visually what you're seeing right now is that COVID would have had an effect on the NO2 concentrations. And this goes to say that we're only doing it for NO2 concentrations. So I really invite you to try it for other pollutants and see how that has changed. And now we're going to go to the last section of section 2. Okay, so we're going to run it again, and then we're going to get our chart in our console. So basically, in this case, let's just go to our chart. So we're creating a function to get the mean NO2 for the study region, but we're going to explore the differences in NO2 concentrations by quantifying them because we just looked them as an image. But now we're going to quantify the changes for specific regions. And as part of the code, we calculate the mean NO2 concentrations for Hubei province, and by applying reduced regions to each image in the March 2019, March 2020 collections, and by getting the tropospheric NO2 column number density, which we had seen in section 1, you can get the mean based on the day of year property. And this is what you're building here. So you're creating your get concentration function, and you're creating your image parameter, which you're going to call here. And you're basically calculating the mean. And this function can then be used to get the concentrations for a baseline and a lockdown collection. So this is supposed to give us a time series that we can visualize in the chart. And so it's really, this function is designed to process an image from a collection of NO2 data. It's then calculating the mean for a specific region, and it's returning it in a specific format, which is an EE feature. And then you've got the concentration, the DOI, the type. And this is going to help us analyze NO2 levels over time. As you've got the collection label that is either the baseline or the lockdown, and the image, which is representing an individual image from the NO2 collection. So here we've got the NO2 ag change for plotting, NO2, or filtering by date. So 2020 get concentration for lockdown, 2019 get concentrations for baseline, and then we've got the null. And the null line filter is basically filtering the merge results to remove any features where the NO2 concentration is null. And this ensures that only valid data points are kept for plotting. And then, as you've seen in many chapters, we're plotting. So in this case, there's variations of the UE chart, but if feature groups, we've got the NO2 ag change for plotting. We've got 2 different types of things we want to plot. But from our collection, from our function, sorry, we have the feature on how we want to present this result. And this is our structured format for our information. We've got our title, and then we've got our print. So, okay, so you've got your increasing concentration here, and then you've got your DOI here. 60 to 90 is going to be a 30-day period because basically you're looking at March 2019, and then you're looking at March 2020 for the mean NO2 concentrations. So acknowledging that significant differences could be due to environmental factors, still, we're going to consider what we had seen in our map here, where already from a color point of view and just observational, you can see that there's a drastic change happening here in the NO2 concentrations comparing these 2 months. So is that what we're seeing in this chart? Here you're looking at the baseline. This is our left. Let's say we'll use the inspector tool to look a bit at it. We use the inspector. Okay. So let's say we zoom out, we look at the inspector, we pick, let's say this point. We've got a 0.0009, which is about what's happening here. And then You look here, what's this area here? The same 009, you've got a 004. Again, it's going to be an estimate because I'm kind of clicking anywhere. But you can see that there is a change. And from from the beginning to the end, there are peaks, a lot more peaks than what's happening here in the lockdown. So somewhere throughout the month, there were more NO2 concentrations happening for some reason. But this is just to show you that from both a visual perspective, from an image and from a chart, you can see that there is a change, there is a difference between the baseline and the lockdown. And this is really important to consider when we think of COVID and its impacts both on the environment, climate change, um, air pollutants, although it had significant health impacts on the global population, it did have impacts on other things. And so I invite you to look at other pollutants to look more into it. Okay, so in conclusion for this analysis, this section's focus was on comparing NO2 concentrations during the COVID-19 lockdown in 2020 with those in March 2019 with the baseline, which we just observed. Um, Specifically over Hubei province. And as mentioned, the reason we compared it with the same month is that in different years is because it partially controls for seasonal weather variations, although weather effects will still or may still influence the results. But using Earth Engine's visualization tools like a split panel map to compare NO2 concentrations can help us visualize and understand the changes during the lockdown because you can just scroll through what's happening. And this is important to know, and that's why this is like an additional thing that you're learning from this section, because there's different ways that you can visualize results. And we also then quantified these differences by calculating the means of NO2 levels and presented them in a time series graph, which we did up here, and for both March 2019 and 2020. So we go back to our chapter. Um, so this analysis highlights how satellite data and Earth Engine tools can be used to visualize and quantify changes in air quality, especially in this case for NO2 concentrations. And there are assignments in this chapter where you can try different um, elements and gases and not just looking at NO2, because this can be applicable in other cases. But here we're looking at a significant event like COVID-19 and the lockdown and looking at what kind of changes in concentrations have happened. And by comparing the same region in Hubei province, but for different months in different for the same month but different years, that allows us to observe see potential reductions in NO2 levels during the lockdown. So while weather conditions can still impact pollutant concentrations, these visual and quantitative methods really provide valuable insights into how lockdown measures, for example, like the one we lived for a while, can affect air quality. And you can apply this to other regions, other pollutants, and this is just an introduction to what you can do with this kind of data for other environmental impact studies. And so then we're going to go in section 3 just to add an additional point to this section and to this chapter, which is calculating population weighted concentrations. And the reason we're doing this population weighted concentration, I'll explain later, but it's because it's not as accurate to just do a simple average, especially if you have population diversity. So we're going to be calculating the population weighted exposure across n pixels in the area to avoid a skewed representation. We're going to map a function to calculate population weighted exposure over all the images for the NO2 collection for a specific year. We're going to look at the contrast between the simple average and population weighted average. And this is because we're going to see what the difference is because, for example, in red, you'll have the average and in blue, you'll have the weighted average. And I'll explain why, but it really has to do with how the population is dispersed and how much population you're dealing with in specific areas. And then just to finish off, there's easier ways to process data, although there's a lot that can be computed in Earth Engine. There are easier ways if you convert the data to a CSV, for example. So we're going to convert the data to a CSV file to Google Drive. so that then that can be used in R or Python. And it's just different ways of working with data because you can create a time series in Earth Engine. You've done it in many times in other chapters, but it's important to explore other ways to visualize data because it's possible. So to do so, we're going to go an A14C checkpoint because that's for section 3, and that's going to end our chapter. So again, you're going to go down here, section 3, under the checkpoint, and just copy this, and then copy paste into your new script. Okay, so let's get into the code. And I'm just gonna take my camera away for a sec. Okay, so before we look at this code really quickly, just recall, as I mentioned not long ago, we're going to be working with this equation specifically. And so we're going to translate this equation into this code. And that's the biggest part of section 3. So if you remember in section 2, we used the reducer mean in reduce region function to get the average NO2 concentration over Hubei province. So this is when we calculated the mean. But the thing is, when you're aggregating pollutant concentrations to define population exposure, there requires a different approach. And this is because if you imagine there's a large concentration of NO2 in a rural area in the east of Hubei province where few people live. You won't see it here because we redid the panel, but let's say it's in an area where not a lot of people live. And from that, we just calculated the average of all pixels. Then if you have this area where there's few people that live there, then this rural NO2 anomaly would skew our representation of population exposure. So using the population number data set that we imported in section 1 out here, we're going to calculate the population weighted exposure, exp, aggregated across n pixels in the area of interest, which is in this case is Hubei province. So if you look at this equation, you're calculating for exp using this equation, and Ci here is the NO2 concentration, and Pi is the subpopulation in pixel I. So go back to our code. So we're going to be mapping, so we have our scale population. Remember, this comes from the data set that we're using. And remember when we had looked at the different population data sets, there were different resolutions. And for gridded population, it's 927.67. So that's why we're setting our scale as that. And then we can calculate P outside of the function because we have the population data. And we're going to do that so it's not computed multiple times for each NO2 image. So this is the first thing we're do. We're setting our population variable, summing it up, and we're going to have, that's going to give us our population count that's outside of our function. So then we can use it later on because we have population. So now we start our function to calculate population weighted exposure. We're going to do that over all the images in the NO2 image collection. So if you remember, let's see, the first thing here, so remember CI/PI, which we just determined. We've got P here as our population. We've got the region name. This is us building our population weighted concentration function. And the first thing you want to do is calculate the percentage of valid pixels in the region. So if you remember in section 1, we had masked out pixels from images that had a cloud cover value greater than 30%. And so what's important here is to calculate the percentage of available Sentinel 5P pixels within the Hubei province per image, so that with the percentage pixel coverage that we have, it's enough to calculate a representative average for the province. So here, what you're doing is, again, you're picking up the non-masked pixels. So here with the CI is the image GTE, it's checking if the pixel values in CI are greater than or equal to 0. This creates binary mask, and pixels that are valid are going to be greater than 0, will have a value of 1, and invalid pixels will be smaller than 0, and it will have a value of 0. The same thing you're doing for the mask here. It's replacing any pixels that are not defined, masked out with 0. So if there's any missing data in CI, those won't be treated, they'll be treated as invalid pixels. So you've got a reducer mean here, our population, and then we're getting the tropospheric NO2 column. We've done this before, so you should be aware. See, we literally did it in section 2, and this comes from the band for this imagery. Then you're calculating the per pixel X. So really what we're just following this equation, but we're writing it out as code. So you're doing the sum, and then you're calculating the mean NO2. And so what we're doing here is we've got the population weighted exposure, and that's aggregated across n pixels. And then we are calculating the mean NO2. And this section is the approach that you take without population weighting. So this is literally just calculating the mean. Like we talked about earlier, let's say you were doing a population average. However, here we have the population weighted. So you've got these two that you're building here in your function, and that is then translated here when you're returning a feature with properties. This is going to be important because you've got your system time start, where it's retrieving the timestamp from the image object, the IMG, and it's assigning it the system start time start property. Then you've got the var feat out. What is that? It's just creating a new feature. And the first argument null here is just indicating that the feature doesn't have geometry associated with it. It's just a collection of properties. And here you've got the date string, and this is just assigning a format to the date. You've got the region name for what's being analyzed, and this is your important part. So here you've got exp sum, which is your population weighted exposure, and I've got the NO2 concentration raw, which is just the population average or without population weighting. So it's just not a population average, but an average of NO2 concentration. So then you're going to filter the NO2 collection for March 2020, and you're going to map the function over it. So the no2 ag pop weighted is going to be what we created. So you're going to create your variable for NO2 aggregation population weighted. You're going to filter the date for March 2020, and then you're going to select the admin unit Wuhan and then turn it into a feature collection. Then you're going to define the percentage of valid pixels you want in your region per time. Here we're choosing 25, and that means that only images with at least 25% valid NO2 pixels will show up. So in this case, we chose 25 because for illustrative purposes, but if you have a specific research question, then you might want to calculate averages only when you have 100% coverage by Sentinel 5P that is free of clouds. So in this case, we're saying to play around with 25, but I suggest you play around with it and see what you get and whether or not that allows you to calculate a representative average for the province. So again, here you're filtering the feature collection based on your pixel criteria. So greater than or equal pixel cover purse. Valid pixel purse, but you're calling it pixel cover percentage. And then you're printing the population weight in NO2 feature collection. And then this is just you calling your variable. And then you're creating a feature collection for plotting the mean and the mean populated weight. Because what we're going to compare is when we consider population in the average of the NO2 concentrations, is it different than when we're just plotting the mean NO2? And we're going to do that on the same graph. So this is just setting your variable, setting the function, and then once you've done those, merging the NO2 concentration raw with the NO2 concentration populated weighted, then you can make your chart. And again, this is just the basic charts. So you're setting your chart type, giving your title, and then printing. We're going to take this out because this is going to be the last section. So let's just run it and see what kind of chart it gives us. So what's happening here is that, or what we should be seeing is that we have pixel cover percentage, which is coming from valid pixel purse, which we just did here. And that stores the percentage of valid pixels as a property of the feature. And the chart that we're supposed to get is the raw versus pop weighted. And the chart we're seeing is demonstrating a contrast between the simple average and the population weighted average for Hubei province in March 2020, focusing on Wuhan. So in this case, the difference appearing a bit small, but when you're aggregating over large areas with a greater variation in population density, this is where the population weighted average shines and can be different, very different from simple averages. So, already, although it's small, you can still see that there is a difference. Even then, it seems like when you're just doing the mean NO2 concentrations, there's not as many peaks as when you're doing the population weighted in between the dates. So clearly there is a difference when you weigh population in the scale, and it just makes it more accurate. Again, play around with the validity of the pixels in terms of cover. In this case, we just took 25%, but playing around with that, and that might alter your results as well. And then in the last part, we're going to export the population weighted data for multiple regions, and we're going to export it as a CSV into a Google Drive because we can plot this data in Earth Engine, but it's usually often easier to process with other statistical software like R or Python. So we're going to export as a time series and just have it be used in other softwares. But basically, you're mapping a function over the regions that calculates population weighted NO2. And this is the function, the no ag2 multi pop weighted, because originally you just had the no2 ag pop weighted. And so this is just defining based on your regions and your mapping. You have a function region. You've got var p. And if you remember, we had done this earlier. Population, reduced region, you're summing your population. And then that's what you're doing here. And then you've got your population count. And then you've got your inner table variable, which is your NO2 concentrations being filtered by date. So March, again, same dates as we used earlier. And then you've got your population weighted concentration with which we had done here. So you're just calling it back again. But you're saying region, however, in this case, we had just one region, which is basically the Wuhan and the geometry. And in this case, we want the region to be from admin name and specifically these two. And then you return in a table, and then you go on to filter out readings that have pixel percentage cover below your threshold, which in this case, our threshold is 25. So this is important to keep because otherwise you're going to get different data from what's happening here. It's just making it consistent. And once you've done that, you can use the export table to drive function in Earth Engine. And then what do you want? Your collection, your feature collection, we created it earlier. And then the description, what it is, and then we can run it. And this is going to appear in your tasks because you can then find your CSV in your Google Drive later on. So let's say I run this. I can keep the name. I can name the drive folder if I want, and or blank for root. So if I just do blank for root, as you can see, it's struggling. So what you're gonna do is open in Drive, and then you got your CSV here. So really what you just have to do is the phase is completed, you can run it, and then you can open in Drive. Close that, and then feel free to try it out in R or other things, other softwares that you think you could use your CSV in to see what this gives for different areas. Okay, so that concludes our section 3. We've just ended this chapter on assessing population exposure to air pollutants, and in this case, using a population weighted exposure rather than simple averages, which I explained why. But again, a simple average of NO2 concentrations could have been misleading in our case, especially if pollutant levels are high in sparsely populated areas. And this is because it overestimates the exposure for the general population. So by using our well, in this case, by using The population weighted calculations were ensuring that exposure estimates reflect areas where more people are affected. And this method that we combined with cloud-free satellite data, or as much as possible, provides a more accurate representation of pollution's impact on human population. So even though the difference between these methods of the average and the population weighted can seem small in specific cases, here you can see like it becomes specifically significant when you consider regions with diverse population densities. And this makes it an approach that's vital for public health assessments and policymaking because you want it to be as accurate as possible. And already we've examined the differences in between these two types of averages. And so after doing that, we then learned how to export it as a CSV into Google Drive. And that's just an additional learning component because we know that we can plot the data in Earth Engine, but it's often easier to process with other statistical software like R or Python. So that is the end of this chapter, as I mentioned. So let's do like a little recap. So we've covered the basics of importing Sentinel-5P air pollution data. We created a split panel map. We compared changes over time, and we calculated a population weighted average for spatial units. And we compared it with also simple averages. And you should have learned from this that satellite detection is crucial for monitoring air quality on local to global scales. The ground station measurements and atmospheric modeling are key for assessing human health risk. The combination of satellite and ground level data with advanced machine learning models to map and forecast air pollution is a growing research field. The fusion has important societal applications like air pollution forecasting, and Earth Engine is a valuable underutilized tool in this field. This should provide you with, as I mentioned, enough detail for how to use Earth Engine with Sentinel-5P, but also we looked at other data sets at the beginning. There's more than that, so I invite you to look at those other data sets, explore what you could do with those. We looked at the offline in this case, but I invite you to do other ones, like the NRTI. There's also other pollutants, as I mentioned, with the Sentinel-5P. We just looked at NO2, but there's a lot different more. If you're going to look at methane, however, there is only offline. But look in your area as well. See if you can translate everything we've done in your area and make comparisons. Again, it's best to do month at the same month, different years if you're going to do that, because of the weather effects. Consider that clouds and weather is also going to impact your pixels. Your resolution is going to impact what you use for your population data, for example, is going to impact. So think of all those things that we've gone through as well and how your data can change and be variable. And with that said, that's it. So thank you.